Hello, Astronomy. Mr. Janowski here. This is part 7 of the chapters 14 and 15 slides. In the last part, we talked about the corpses of the low mass stars. So, when a low mass star dies, the outer layers drift away in a planetary nebula, and you're left with just the dead core, dead in the sense of not doing fusion, core of the star, and that's what's called a white dwarf. So, now we will start to talk about the corpses of the high mass stars, of which there are two different types. So, we will talk about the corpses of the lower mass, high mass stars. So let's get started with that. Loading. Slow computer. So the corpses of stars, white dwarfs, neutron stars, and black holes, are known as, well, I keep calling them corpses, but an astronomer is more likely to call them compact stars. So all three of those things are not actually living stars. They're not doing fusion in their core, but we still call them compact stars. So, what is it that prevents gravity from crushing a white dwarf? So, while the star is alive, you've got pressure from nuclear fusion counteracting gravity and keeping gravity from crushing it. But this is a dead star, so no more fusion. So, what is it that keeps gravity from crushing it? It's this weird thing called electron degeneracy pressure. So, here's Wolfgang Pauli, who, if you took chemistry, you might have learned the Pauli exclusion principle. It's basically why chemistry works, why electrons do what they do in atoms. It's a complicated quantum mechanical kind of thing. Ultimately, it's physics. It's all physics, ultimately. You know that by now. But anyhow, electron degeneracy pressure is strong enough to prevent gravity from crushing the white dwarf. So, what happens if a white dwarf with a binary companion goes over the Chandrasekhar limit? You get a big boom. This is a type 1a supernova. So, here we have the white dwarf is in here. It's got a binary companion. So the white dwarf is still very massive, so it's stealing material with its gravity, and it's all collapsing onto the white dwarf. If it collects the material too quickly and it goes over this Chandrasekhar limit, then you're going to have this big boom, and the white dwarf is going to go bye-bye, as indicated by this X right here. No more white dwarf. So the companion remains. It's likely, because it was orbiting this guy and going around in a circle, well, the thing was orbiting is suddenly gone, having blown up in this Type 1a supernova. So now the companion just kind of shoots off through space, indicated right here by this little arrow right there. So yeah, that is the corpses of the low mass stars. So back in 1932, physicist, you think I'd be able to say that word, physicist James Chadwick discovered the neutron. So yeah, kind of odd. If you think about how kind of basic and fundamental the idea of electrons, protons, and neutrons are, that's fairly late to have discovered neutrons actually exist. They're hard to detect. They don't have a charge that makes them hard to detect. But anyhow, yeah, 1932, James Chadwick discovers the neutron. 2 years later, astronomers Walter Baade and Fritz Zwicky predicted that some high mass stars could collapse into neutron stars. So here's Walter Baade. Looks like a perfectly nice man. And here's Fritz Zwicky, who is not a perfectly nice man. Fritz Zwicky, wonderful name, first of all, is a bit of a misanthrope, or misanthrope, I guess is how you would normally pronounce it. So, yeah, kind of a cranky, cantankerous fellow. Still very entertaining. I mean, that's just a wonderful picture of him there. So here's one quote from him. Astronomers are spherical bastards. No matter how you look at them, they are just bastards. So what is he saying there? Spheres are the one shape that no matter where you're standing relative to the sphere, it always looks like a sphere. If you picture a cube or a pyramid, if you start to move around it, you'll start seeing different sides and it looks like something of a different shape. Spheres are not that way. So yeah, no matter how you look at a sphere, it's a sphere. So that's what he's, this is a kind of a STEM culture kind of joke that astronomers are spherical bastards. No matter how you look at them, they are just bastards. So let's start this one with the other Fritz Zwicky quote. I myself can think of a dozen ways to annihilate all living persons within 1 hour. So yeah, he's the kind of person that would say something like that. Most people with enough training in STEM and especially physics, yeah, we can do that. A dozen ways to annihilate all living persons within 1 hour. Yeah, that wouldn't be that difficult. But yeah, anyhow, Fritz Zwicky, misanthrope. So White dwarfs are the remnants of low mass stars, and they are made of carbon and oxygen. So these low mass stars, they never got hot enough to fuse things beyond carbon and oxygen. So these cores are just carbon and oxygen. So if you've got this white dwarf with its binary companion and it pulls too much material on here, suddenly you're going to have too much stuff. It's going to overcome the electron degeneracy pressure, and the whole core is going to collapse, and it's going to get hot enough to fuse the carbon and the oxygen. So yeah, everything that's in here is going to undergo fusion real quick, and you're going to get this enormous type 1a supernova. And the white dwarf is going to be annihilated. So no more white dwarf. The corpse has blown itself up. And the key idea here is it's because the core of this star, the white dwarf, has got carbon and oxygen in it, and not any of the heavier elements, because the living star never got hot enough to fuse things beyond that in its core. So high mass stars are going to be different. So remember, they have a different kind of life cycle, and the high mass star in its core, when it dies, is going to be made of iron. So we have a lot of iron in the star. So what's going to happen in this case? So the star dies, it stops doing nuclear fusion, so nothing is counteracting the gravity. So very rapidly, the outer layers crash down onto the core. They are going to reach fusion temperatures, and the whole thing, not the whole thing, the outer layers are going to explode in a type 2 or core collapse supernova. So that's the outer layers. The important idea here is the core of this star is made of iron, and it's not going to get to the temperatures that are hot enough to fuse iron. So the core is going to remain. With our dead low mass star, its core is carbon and oxygen, so when everything collapses down onto it, the whole thing will blow up, and that's a type 1a supernova. In this case, because the core is made of different stuff, it's made of iron, the core is going to remain. It's not going to fuse. It's not going to explode. So we still have the core. So when we're talking about the white dwarf, electron degeneracy pressure is strong enough to counteract the tremendous gravity of all of that mass crushing down on the star. So in this case, we've got more mass. This is the core of a more massive star, and it's made of iron. So this is a much more massive star, and it turns out that electron degeneracy pressure is not going to be enough to counteract gravity. So these things are going to squeeze down even harder. It's going to beat the electron degeneracy pressure. So what happens, it's kind of weird, is if you think of, the picture of an atom with the nucleus in the middle and the electrons going around on the outside, gravity is going to crush this thing down so much that the electrons that are outside of each of the atoms are going to get crushed into the nucleus. So here's what we have. We have in the nucleus you have neutrons and protons. What's going to happen is the electrons that are supposed to be outside the atom going around are going to get crushed into the protons, and their charges are going to cancel, and they're going to leave you with a neutron, and also this little guy, a neutrino. So yeah, that's weird. And now the neutron star is going to be supported by a different kind of degeneracy pressure. This is neutron degeneracy pressure. So this is, kind of similar. This is a quantum mechanical thing, and the same basic principle holds. Neutrons don't like to be squeezed together either. So yeah, that's what your pressure is being provided by. So the key idea here is white dwarf, electron degeneracy pressure is enough to beat gravity. If you have a more massive star, electron degeneracy pressure is not going to be enough, but you will eventually get to having neutron degeneracy pressure, and this will be enough to counteract the gravity. So yeah, last time we talked about white dwarfs, and white dwarfs are very, very dense. So they're going to have more than the mass of the sun. Well, in some cases, more than the mass of the sun, up to 1.4 times the mass of the sun, squeezed into something that's only about the size of the Earth. So look at this image up here. So this little arc is suggesting the size of the sun, and the mass of that star is going to get crushed down into something that's only about the size of the Earth. And electron degeneracy pressure is strong enough to prevent it from crushing down further. Neutron stars are crazy, crazy dense. They're going to have even more mass, and they're going to be squeezed into a much smaller volume. So you're going to have, 1.4 times the mass of the sun, up to about 3 times the mass of the sun, squeezed into something that's only 20 kilometers across. So only about the size of a city, basically. So maybe you can recognize this aerial view. Well, here's Manhattan, and here's Brooklyn, and there's Staten Island, and Queens, and the Bronx is up here. So this is New York City. For some reason, they'd like to compare neutron stars to New York City. And it gets really weird. So if you had a 1 inch, I'm trying to remember from the last video, if you had a 1 inch by 1 inch by 1 inch cube of white dwarf stuff, that would weigh as much as a car. So yeah, that's a lot. If you had a 1 centimeter by 1 centimeter by 1 centimeter cube, so basically just the size of a dice of neutron star stuff, that would weigh as much as Mount Everest. And keeping with the car example, that one, that dice-sized piece of neutron star would weigh as much as all of the cars and trucks in the United States. So, yeah, these things are crazy, crazy dense. So this picture, hopefully I don't have to tell you this didn't actually happen. We never had a neutron star land on Queens. What would happen if this actually occurred? It would be crazy, because you have the Earth with, it's fairly large mass. Well, this thing right here is actually going to have about 500,000 times the mass of the Earth. So if all of a sudden this guy just showed up here, hanging out over Queens, what would happen? It's got way more gravity. It's got way more mass. It's going to pull all of the things off of the surface right over to here. And this is going to be enough gravity to just basically rip the entire Earth apart. So not only is everything on the surface going to fly towards this, the surface itself is going to fly towards this, and the whole Earth would rapidly stop being a sphere. It would all just kind of collapse onto here. It would be a big mess. So, yeah, let's hope this doesn't happen. I'm not too worried. So, again, Bade and Zwicky made this prediction back in 1934, and it made sense, but it only made sense on paper, and nobody had any evidence for it yet. So that changed about 30-some years later with the help of this discovery by Jocelyn Bell, who was just a graduate student at the time. So here is a young Jocelyn Bell, with a big radio telescope in the background. So, what happened with Bell and her group? They discovered this odd radio signal with this rapid pulse, and rapid and very precise pulse, that went up and down about once every 1.33 seconds. And this was very weird. So when they discovered this, they assumed right away, well, there must be something wrong with our instruments. Something's gone wrong. Because there's nothing in nature that does this, that rapidly goes up and down with this very regular pulse of 1.33 seconds. Then eventually they figured out, well, it's not the instruments. The instruments are doing their job. So they kind of jokingly, they assumed it wasn't this, but this seemed artificial. This seemed not like a natural thing. This seemed like something that was made by an intelligence, not people, by little green men. So they half-jokingly named this signal LGM1 for Little Green Men 1. So here's the Great Gazoo from the Flintstones. Nobody knows the Flintstones anymore. But yeah, this seemed totally artificial. Like maybe this was some alien civilization's technology doing something, making the signal. So they said it looked like it could be that, but they knew deep down it wasn't that. So in fact, it wasn't actually that. So what was causing the pulses? So this is neat. This is going to bring together a lot of the physics that we discussed earlier in the year. So yeah, what's causing these pulses? So think back to the figure skater trick. Remember the thing with the spinning chair? So the skater she goes around, has her arms out, she's spinning kind of slowly, and then when she brings her arms in, she starts spinning much more rapidly. This is called the conservation of angular momentum. So the exact same thing happens when a star collapses. So you have this big star here, and its mass is spread out over this giant sphere like this, and it's all spinning, and it's spinning kind of slowly. Maybe it takes about a month to go all the way around. So when all of this mass collapses, and some of it gets blown out in space, but some of it's going to still be there. When this mass collapses, this is exactly like the figure skater bringing her arms in. So, yeah, figure skater brings her arms in and has to, start spinning faster to conserve angular momentum. When the planet brings its arms in, it's going to start spinning way faster because it's going from this huge shape, its arms are way out there, to this incredibly dense little tiny shape. So, yeah, it's going to spin like crazy. So now this thing's spinning around very, very rapidly. So how does this lead to these pulses? So this thing is spinning very rapidly, and it's got a magnetic field that's going with it. So notice the magnetic field doesn't exactly align with the axis of rotation. This stuff gets just crazy weird. So yeah, this thing's spinning around very rapidly like this, and it's shooting off kind of these beams from its magnetic field. And the analogy is this is a lot like a lighthouse. So if you can picture in this picture, if you can imagine in this picture, you've got a boat out on the ocean and it's looking towards the shore and it sees this lighthouse. Well, the lighthouse isn't turning its light on and off. What the lighthouse is doing is shooting out its light in two beams like this, and it's rotating around, or the lenses are rotating around to cause this. So it's not that the pulses are from the thing going on and off, it's that it's shooting it out in these beams and it's rapidly spinning around. And when the beam happens to be hitting the ship, it seems very bright. And then when the beam goes off the ship, it seems dim again. So the exact same thing is happening. I wish this stupid little thing wouldn't pop up every time I went to the bottom of the screen, but what can you do? So the exact same thing is happening with this neutron star. When these beams are pointing towards you or pointing towards the Earth, you're going to measure a very high signal. And then it rapidly goes off of you and goes around, and then you get the other one coming towards you. And it's just like looking at a lighthouse. And when the light comes towards you, you see this bright pulse. So if that beam happens to hit the Earth, you're going to get these pulses. So obviously, if this thing is spinning around and the beams are always missing the Earth, it's not going to seem to pulse from Earth. But yeah, if the pulse happens to go towards the Earth, you're going to see these pulses. So this is what a pulsar is. A pulsar is a rapidly spinning neutron star whose radiation is detected in rapid, precisely timed bursts. So again, it's not that the radiation is going on and off. It's that the radiation is basically constant, but it's shooting out in these beams. And when the beam hits you, you see the pulse. And then when the beam's missing you, you see nothing. So that's what's going on here. So we've seen this image before. This is the Crab pulsar at the center of the Crab Nebula, which was first witnessed on Earth, I believe, in the year 1054. So we talked about this in the last chapter. But yeah, at the center of the Crab Nebula is a pulsar. So this is the core of the star that blew up to create the Crab Nebula. And it's rapidly spinning. And the one that Jocelyn Bell, that she and her group discovered, that one was going around about once every 1.33 seconds, I believe. This one in the Crab pulsar rotates 30 times a second, which means this GIF that we're looking at is actually in slow motion. Because if we watched it at 30 times a second, that's too fast for you to notice that it was actually pulsing. So here's a slow motion GIF of this thing pulsing on and off. So yeah, the one Jocelyn Bell found, 1.33 seconds was its period. This one goes around 30 times a second, so its period is about 0.03 seconds. And they have some that go around faster than that. There are neutron stars that rotate, so they're pulsars, that rotate at hundreds of revolutions per second. So yeah, crazy stuff. So here are some videos about this stuff. A couple of good Kurzgesagt ones too. So I'll put links to these in the description. Yeah, watch the Kurzgesagt. Always interesting stuff. These things are just crazy. So thinking back to mostly last time, what's the upper mass limit of a white dwarf? That is the Chandrasekhar limit, 1.4 times the mass of the sun. So that's as big as a white dwarf can get. And what prevents gravity from crushing a white dwarf? Electron degeneracy pressure. So that's what supports a white dwarf against gravity. So what's the upper mass limit of a neutron star? About 3 times the mass of the sun. So that means the living star itself was about 20 times the mass of the sun, and its dead core of iron has a mass of about 3 times the mass of the sun. And that's as big as a neutron star can get. And what is it that prevents gravity from crushing a neutron star? Neutron degeneracy pressure. So, yeah, interesting stuff. So now we've talked about two of the corpses of the stars, and they're becoming more and more interesting each time. So white dwarfs are the dullest of the three, but even those are crazy cool. And then today we talked about the neutron stars, and they're even more extreme and more intense than the white dwarfs. And so in the next part, we will talk about the final kind, and just a super interesting thing. The corpses of the high mass stars are black holes. So hopefully you found this part interesting.